Yes, we can see. Yes, okay. We can see your screen.
So I just have one more thing to organize here. Let me see if I can get this right.
We can see you.
We don't see you, Professor.
I tried to make that possible a moment ago, and it told me that the host had my video turned off.
Oh, okay. Sorry, we turned you off because of the talk. Now it's working?
So.
Yeah, okay, we can see you now.
You see me?
Yes, thank you.
Okay, I'm very sorry for that. Okay, are we all right? Should I start?
Yes.
Okay, very good. Thing to organize, yes. Right, well, good morning to everybody. And I have to say that I am very sorry that I am not there. And I hope that on a future occasion, I will be able to be there again. And let's see how things go. Right, so this is what I'm talking about, binary neutron star coalescence after the merger. And I think you'll all know which particular object I'm going to be talking about. I'm going to be using that one as an example, we hope, for a whole lot of future sources which are along similar lines. So first of all, let me just mention the historical background to this. In 2015, we had the first direct detection of gravitational waves, which was the binary black hole coalescence. The numbers that I've put on this slide are mid-range numbers. There are error bars on the numbers, but I'm taking the middle for the purposes of this slide. And in that first example, we had 2 black holes, 36 solar masses, and 29 solar masses. And the object was at just over 400 megaparsecs from us. That was the first one. The next one that I'm mentioning here is 2017, the first detection of gravitational waves from a binary neutron star coalescence. So of course there were other detections as well, but I'm picking out these particular ones. That is the object that I'm focusing on today. This is known as GW 170817, a number that sort of impressed on my brain. 17th of August, 2017. And this was the first binary neutron star coalescence. And the mid-range values for the masses were 1.48 solar masses and 1.26. And the object was at 41 megaparsecs. So notice that's 10 times closer. The masses are less, the distance is much less. With both of these two sources that I've talked about, they were both quite strong signals. But the second one was strong because it was closer. Then also I should mention, for the purposes of today, the second binary neutron star coalescence detection, which was in 2019. This is the first one that is considered by everybody to be a believable one. There were a whole lot of others that were suggested as possible detections, but on rather weak evidence. That one, 2019, had higher mass neutron stars. One, 1.75 solar masses, the other 1.57. And that was further away, 4 times further away, 161 megaparsecs. That was seen far less well. Whereas with the GW 170817, we not only saw the coalescence in gravitational waves, we also saw a short gamma ray burst and very extensive multi-messenger observations. which enabled us to tell a whole lot about this source. So for the purposes of today, I'm using that as my main example, because that's the one where we have the evidence right now. But I hope that I'm going to be able to say things which are of more general relevance for future sources that hopefully we will see of similar sort. Okay, so let's come on to saying something in a little bit more detail about GW 170817. This is what we saw. We saw gravitational waves from the in-spiral of two neutron stars with probable masses. I'm giving here the ranges. Ranges are actually quite wide. The thing that we know rather well is the combined mass of the two objects. It was followed by a short gamma ray burst, which came 1.74 seconds after the gravitational wave signal. And that is an important number and a surprising number. Why the delay? Why was it as big as that? And that's one of the questions that we'll be talking about. This is 1.74 seconds after the inferred time of the coalescence coming from the gravitational wave signal. The actual coalescence was not seen in gravitational waves. The reason being that the frequency of the signal at the time of coalescence was too high for the detectors. It was outside of their sensitivity range. So that the actual coalescence was not seen, but we saw enough of the in-spiral to be completely sure what was going to happen. As I mentioned a minute ago, this was rather close to us. In fact, it's often referred to by people as being almost next door to us. It's sufficiently close, but you have to have some scale for saying these things. 41 megaparsecs, we're talking about a redshift, which is 0.008, which in cosmological terms is not a lot. The fact that it was close made it easier to see. However, we should be careful about what we're meaning by things here. Later on, we're going to be talking about some rather recent observations which have been made public in the last months. And these are things that we see with the progress of the development of the source with time. And we're seeing that in our time on a time scale of months. So we're watching the thing progressing, which is rather a spectacular thing to be saying. We're looking out now for the next data point to put on the figure. And we expect that rather soon we're going to be told that one. And then we have to wait for the next one. But something you have to bear in mind is 41 megaparsecs. This is 130 million light years away from us. So what we're looking at is light that was emitted 130 million years ago. But we're looking at a time sequence which is separated on a human time scale of weeks, months, and so on. So this object is something that we're referring to as being close, but we're seeing something which is really in human terms very far away. And it's worthwhile saying that in the early days of thinking about gravitational wave sources, before we had any observations, people were thinking particularly in terms of supernovae as possible sources of gravitational waves. And at that time, a number that was often mentioned as a distant scale was 25 megaparsecs, which is the distance out to which you're seeing all the things from the Virgo cluster. And it's thought that you could have a high event rate for supernovae if you could see out to that scale. But what we're talking about here is further away than that. So just to give an idea of the scale. Okay, here is the picture of what was seen at the time of the burst. At the bottom here, we have the gravitational wave signal. And what is being plotted here is frequency against time. Whoops, against time. And I should say this was a very strong source. The signal to noise ratio was more than 30. A lot of the gravitational wave signals are fairly weak, but this is a really strong one. So there's not been a lot of messing around has gone on in presenting this picture. This is pretty much what you see. That's what we have at the bottom. At the top, we have the light curve as seen by the Fermi gamma ray burst monitor. And there you see the peak in the gamma rays happening with this gap after the gravitational wave signal. So let me just say another word about the gravitational wave signal. What is happening here is that as the two neutron stars come together, there is angular momentum, orbital angular momentum, which has been taken away by the gravitational waves. They spiral closer and closer together. They go faster and faster. Roughly speaking, you have conservation of angular momentum, so you decrease the distance between them, and at that stage, the thing goes round faster. It's only rough conservation of angular momentum, but gravitational waves are taking away some of it. So that gives the right picture. So the frequency is going up, and this is the well-known chirp signal with rising frequency, like that. Okay. So this is what was seen, and that is the time of the pulse. After that, there were various other things that were seen. And this is where the so-called multi-messenger observations come in. Optical, X-rays, radio, and so on. After about 10 to 12 hours, we started seeing optical observations. And I think it's really quite incredible that you could localize the object. And here you see these little lines marking the position of the gravitational wave source in the outskirts of the galaxy that it's associated with. And that you can see in some of these frames really quite clearly, particularly in this first one. So this is something that one started to see after 10 to 12 hours after the initial signal. Then, after a number of days, one started to see signals in X-ray, radio, and some other frequencies. And here is a Chandra observation in X-rays, and this one is JVLA in radio. Now, these observations are telling us about radiation, which is basically coming from the jet, which we'll be talking about, which is associated with the source. First of all, the jet is obscured by matter which is around it. Then it breaks out from the obscuring matter, and then it can move freely. And through most of that time, we find that the radio observations follow the same sort of light curve as the X-ray ones. It's the same shape, right until recently. Okay. So here is a picture which is showing what is happening to the neutron stars as they come together and merge. this is coming from a numerical simulation, but as you can tell, the pictures have been tidied up a bit. One of the things that we know about neutron stars, of course, is that they tend to have magnetic fields. And I don't know how well you can see this, but marked on this frame, you have marks which are showing a dipolar field in each of these neutron stars. And at this stage, the dipolar fields are quite clearly seen. But as the two objects come together and they merge, this nice ordered magnetic field structure starts to get seriously messed up. When the merger has really happened, get to this frame here, you have this enormous crunch as the two objects come together. You have a whole lot of matter which is thrown out away from the central bit. You have very high densities in the middle where there has been the crunch. And of course, that is obscured from view in this picture because it's right down there in the middle. So this is the stage where we actually get the coming together of the two neutron stars and the merger. Now, the bit that you have in the middle of this develops itself into a single coherent object, which is like a neutron star, but a bit different from ordinary neutron stars because it is more massive than an ordinary neutron star could be on its own. It's referred to as a hypermassive neutron star. It's able to be more massive than normal ones because you have a whole lot of random motions going on there, and it's very hot, so it can be above the mass limit that you have for an ordinary neutron star. And so what's going to happen to that is that eventually, as it sorts itself out, and a lot of these random motions die away, it's then going to be undersupported and it's going to collapse. So that is the overall picture of what's going on there. Okay, now this is a picture that you have, which was a calculation that was made before we'd seen this source at all. And again, it's a neatened up picture of a numerical simulation so that you can see what we're referring to as the anatomy of the gravitational wave merger signal. Now, I should say that a number of the pictures that I'm using here were ones that were calculated by Luciano Rezzola and various colleagues of his. And quite a few of these people were at one time or another members of our group at CISA in Trieste. Now, the picture that we have is this. At the beginning, you get the chirp signal that I was talking about earlier. So this is a rising frequency up until the time that you get the merger. If we had two black holes coming together, what you would see there is that you have this rising frequency, and then essentially immediately afterwards, you have a decaying ring down signal, rather like what we have at the end here for our binary neutron star coming together. What happens with the neutron star is that you get this extended period of emission after the merger, up until the time when the central part becomes undersupported and collapses. Now, there's a time scale along the bottom here, and you should be careful not to pay too much notice to that, because it turns out, this is, as I said, this is something that was calculated before we'd seen GW 170817. And the timescale there has turned out to be very different. So be careful in looking at these numbers. So let me just say again, here we have the chirp signal, and this is going from lower to higher frequencies. Afterwards, you get this sort of structure. Now, this is when we are seeing a merged object, which is the hypermassive neutron star. The other thing that I want to point out here is that there's a quite ordered behavior that you see. And these are quasi-periodic oscillations of this central object, which are of very great interest, and which, if we could see them in a real source, could tell us quite a lot about what is happening in the middle. But unfortunately, we have not yet seen any gravitational wave signal after that. So, and then right at the end, you have the cutoff and the ring down. And basically what is happening along here is that the frequency is going up with time. Okay. Now, this is a picture which is drawn in a different way. And this one is plotting, instead of time along here, is plotting frequency. And as I was saying, roughly speaking, these go together. This again is coming from calculations, and again, calculations that were made before we saw this source. Okay, and on this axis, we have the amplitude of the gravitational wave signal. We have these three gray lines, which are sensitivity curves for the detectors. The top one was for initial LIGO. Second one is for advanced LIGO. Roughly speaking, what we had at the time that the detection of 1708-17 was made. The bottom one is for the Einstein telescope, which is a project which has been talked about a lot, but is still a long way off for actually being able to be constructed and to take data. So to give an idea of it, we're not going to be getting data from this until about 2035. There's a lot of work to be done before you get to that, but the planning stage is very much underway. Now I want to point out these three different stages in the signal. First one, which is marked in green, you effectively aren't seeing the structure of the neutron stars in that part. They're effectively point particles spiraling together. And so this line for the signal, the blue one, which is the calculated line, is a very, very simple one. After that, you get into the yellow region. In the yellow region, then the two neutron stars start to feel each other's gravity, and you start to see tidal effects. That's something that was seen in 1708-17. And quite a lot of information has been got from that, from analysis of the tidal distortions that you can infer from the observed gravitational wave signal. The end of the yellow bit, that's where you get the neutron star merger. And then you get to the brown bit, which is the very interesting post-merger regime. And that, none of that we have seen. The curve that is marked here is the result, as I said, of of numerical calculations that are made, which embody various assumptions, which may or may not be right. So it's very, very conjectural, that part. This picture was drawn for a source at 100 megaparsecs. The one that we had was closer than that. But I have to say, I think this picture of the relationship with sensitivity curves was more or less right for the one that we saw. Okay. Now, from the signal that we in fact saw for 1708-17, from the tidal deformabilities that showed up in that, which give rise to the things called the love numbers, one can get a constraint for the radii of the neutron stars. And this was something that was done by the LIGO team in their early papers talking about this source. Subsequently, other people have looked at it. They've tried to neaten up the calculation. And the constraint that they got, which they said really applies to both of these objects, despite the fact that they have different masses, within the uncertainties, they said both of them have radii which lie between 11.9 and, sorry, that should be 14 kilometers, of course. Sorry, no, I'm getting this wrong. Let me say it again. 11.9 plus or minus 1.4 kilometers. And that goes to a range of 10.5 to 13.3 kilometers. Okay. Now, that range, I have to say, is not terribly impressive because it's a very wide range. However, it's interesting that one can get it. And it does actually rule out some of the crazier suggestions for neutron star equations of state. So that's what we've got. Some other people who've come along later and have used other constraints to place together with these have reduced that range. But I have to say that is all very controversial. And so I'm sticking with these numbers, which came directly from the beginning. Okay, I heard a beep there, so I think that was for me. Right. Now, these pictures are showing, this is again from Luciano and his colleagues, are showing the stage where you get the collapse to form the black hole and after. First one is the picture we saw before, and the second one is where you've had a collapse of the central regions. You've got a whole lot of structure that's starting to form. There's a ring which has been produced, and you're also seeing here a representation of the magnetic field lines, which are going to the sort of configuration that you need for forming a jet. So what is happening in this stage? We have a black hole which is surrounded by a centrifugally supported high-density torus, and there's a quasi-spherical cloud of dynamical ejecta around it. You have rapid accretion of torus matter, plus diversion into a jet which is funneled by the magnetic field. The jet is moving out through the dynamical ejecta, first of all, inside the ejector. It entrains some of it to form a high density cocoon that is round the central jet. And the central jet eventually breaks out from the cocoon. This is a picture which is, of course, a cartoon picture, but which tells you quite a lot about what is going on at this stage. This is taken from a review article by Margutti and Shornock. And this is going, I think, into annual reviews. and it hasn't yet been published in annual reviews, and there's still some changes being made to this article, but it can be found on the archive. So this is basically the structure that is inferred for the source. And this is talking now about after the merger, and it's talking about what we infer from the electromagnetic radiation of different sorts. So structure is basically like this. In the middle, you have the site of the coalescence. So you have your two neutron stars that have come together. They've produced their chirp signal. You've then got to this object. In the central region, you have part of this cloud of material, which the outer parts of it are quite diffuse. The central part is extremely condensed. And this is a region where you have matter, which when it was in the neutron stars, had gone to the form of neutrons, protons, electrons, and whatever other particles. It has got smashed together at very high energies. And as a result of this smashing together, you have conditions that were right for forming our process nuclei in the outer parts of it. And it's thought that this sort of object is probably the major source in the universe of our process material that we see also in our galaxy and in our neighborhood. So these are the heavy nuclei beyond iron, the rare earths, the lanthanized, the elements, the neutron-rich elements going up to gold and platinum. So if somebody has a gold ring on their finger, quite possibly the gold was produced in one of these things and has then gone on a journey through space before ending up on your finger, which is a heck of a thought. Okay, now here you have the region of the jet, which has come out from the central object. That jet originally is entirely within this diffuse matter. It fights its way out through that, and then there is a breakout into the surrounding material, the extremely diffuse surrounding matter of the ISM. The jet is ultra-relativistic, has a gamma large compared with 1. The energy is estimated at 10 to the 51 ergs. Outside of that, you have the region of the cocoon, which is also mildly relativistic. The gamma is a few. And out here, this is the region of the kilonova. Out here, you have matter which is being ejected at relativistic speeds. It's faster along the polar direction because there is less resistance to it. The velocities there going up to about 0.3 of c, and in the equatorial direction, it's about 0.1 of c. The other crucial thing to point out is that when you have gamma rays that are emitted from the very central region here, the direction in which it is easy for the gamma rays to get out is along the jet, because you have other material which is all going the same way. That's the easy way to go. When we see soft gamma ray bursts, the short gamma ray bursts, what we're doing is we are seeing them down the direction of the jet. Gamma ray bursts are typically very far away, much further away than this one. This one, we are able to see even off axis the gamma rays. Normally you couldn't do that. You could only see gamma rays coming out if we were looking directly along that direction. So we're seeing much more of the source here than we would see of most sources. This is the angle. And all of the things I'm saying here are based on inferences that one can make through a detailed analysis of the electromagnetic radiation that has been seen, and also tracing back to the gravitational waves that have been seen. There's a whole industry of analyzing this. So this source, as we're seeing it, is not a very strong gamma ray burst. It's not very strong because we're seeing it off axis, and it's weaker if it's off axis. Okay.
3 minutes, Professor. 3 minutes.
Sorry, I'm not hearing terribly well.
3 minutes, Professor.
Oh yeah,
Sorry.
okay. Fine. Okay. I'll keep going. What is the reason for the 1.74 second delay? It could be a delay in the black hole forming. It just takes a long time to get the collapse of the central part. Or it could be a delay in the jet getting out through the bent surrounding matter. But it's a little bit mystifying why it's so long. Some people can suggest that it may be a sign that general relativity needs modification, and that the speed of the electromagnetic radiation is not the same as the speed of the gamma rays. Sorry, let me say that again. The speed of the electromagnetic radiation is not the same as the speed of the gravitational waves. That's a possibility, and it's interesting that there are some alternative models of gravity that are actually ruled out by this. I think that's a little bit far-fetched. Okay, now I'm coming on to the last thing which has been seen very recently. The jet was seen in radio and X-rays, and there are similar light curves for both. And was seen before and after breakout from the cocoon. And the light curves, this is the radio one, looked like this. While the jet was fighting its way out through the cocoon, you have this rising part, flux density against time. And 160 days after the merger, you had the breakout. And at that stage, the jet was free to move and it could expand as it wanted. At that stage, the flux density goes down. This is the picture out to about a year after the merger. This is what we have been seeing in these last months. Up until that stage, the X-rays were going along with the radio. At this stage, suddenly, the X-rays started to increase. The radio kept going down like that, but the X-rays started increasing. And we're waiting for the next data point along with this. I don't have time to go into what these different dotted dashed lines are coming from analytic models. The gray one comes from a numerical simulation. But what we think this is that it is the afterglow coming from the kilonova. So it's radiation seeping out from the really central parts of this collision region, and is therefore extremely interesting. Okay, so summary. This was our first look at the optical counterparts of a gravitational wave source. And we've got a detailed idea of its structure. Multi-messenger astronomy was born, which is great, that you're able to see things in gravitational waves and electromagnetic radiation and put together a detailed story. The binary neutron star mergers were confirmed as at least the sources of some short gamma ray bursts. and also as major potential production sites for our process elements. Let me just recall with the R process, this is something that you get happening when you have an enormous flux of neutrons coming in to the place where you're getting the nucleosynthesis happening, so that you can build up neutron-rich nuclei on a time scale which is short compared with the weak interaction time scale that stops it growing. Okay, all this was great, but it leaves a big question hanging. And the big question is that we'd like to go to higher frequencies in the gravitational waves to look after the merger with them too. And we asked, what would we see then? Might we get some new insights into the workings of fundamental physics coming from matter under those extreme circumstances at the heart of these objects? It's a tantalizing thought that we might get that. The thing which is a little bit depressing is the thing in brackets at the bottom. We probably have to wait for the Einstein telescope before we stand a chance of seeing that, and that is a way off. Just possible that further improvements with LIGO might be able to see something. They already looked hard with the present LIGO configuration for 1708-17. They didn't see anything after the merger. It's just possible they might see something with the later upgrades. I'm skeptical. I think probably it's necessary to wait for the Einstein telescope. That's it. Thank you very much.
Thank you very much, Professor. Now, start the questions.
We have a question from the online, from Sudipta. So, Sudipta, maybe you can start with yours.
Yeah, hello, Professor. Thank you very much for the nice lecture. I have only one query that you might have said, but I maybe skipped it, that one. So after the formation of hypermassive neutron star, how long does it take to form black hole? I mean, if you can comment on this in time scale, in maybe millisecond.
No, but what you're asking here is one of the questions. We know that you have to have an explanation for 1.74 seconds wait in between the gravitational waves and the gamma rays. What is it that caused that 1.74 second gap? Now, one of the things that one can imagine is that you had to wait that long for the formation of the black hole. But that's a bit hard to believe that it would take that long. You'd expect it. All the simulations that have been made suggest that it would be much quicker than that. However, perhaps we're just not understanding the thing well enough. Perhaps it really could be that there is a delay that's that long. And I sort of have a hunch that that might be the answer. However, the other possibility is there could be other reasons why it takes the gamma rays longer to get out. We tend to think if you produce gamma rays down in the middle of the source, they're going to get out pretty quickly, but that's not necessarily true. And some people have suggested that all or part of that delay could be that time, that it's simply difficult for the jet to get going. You really need the jet to get going before you can start getting the gamma rays coming out in an efficient way. So it could be that it's down to that. So this is what I would say, that I think it is uncomfortable asking for a wait as long as 1.7 seconds before you have the black hole. But maybe that's what happens, and we haven't understood it well enough. You'd expect it would be much less than that.
Thank you.
Maybe last question before we go to break.
Well, as usual, in front of this result, you can really use Wigner's statement. Very interesting if true. But let me ask you a question about the statement, the Wigner statement. After all, we know from GRB quite a lot now. And we know also a beautiful example of GRB 90510, which creates a black hole due to very likely merger of neutron star. And we know also that in that case, and in 3 other additional cases, you see very clearly jet radiation, and that the jet radiation now, we believe, on detailed analysis, that there is an opening angle of roughly 60 degrees. I suggest that you look very carefully into that matter for your model. Thanks.
Yeah, no, I absolutely agree with that. This is not one of the things that I'm doing myself, but that's something one should take into account everything, every source of information that can come from neighboring areas. This is very, very important to do in putting together the whole picture. So I absolutely agree with you. And I hope that somebody is looking very seriously into that.
Well, of course, but while you make a review, it will be nice that you mention publication in this topic, which are published in Astronomy, Astrophysics, APJ, and so forth. But it will take, we will have the opportunity certainly to meet, I hope not at a distance, with the improving of the health situation and discuss leisurely and clearly this matter. Thank you. But for the future, just quote the published literature. Thanks.
Okay. Well, I'm limited also with time in what I can do. I mean, as far as this talk is concerned. Also, because of my own knowledge, what I know. But this is something that certainly from now on people should be looking at. I hadn't seen that mentioned in the big review article which has come out about these things. Maybe I missed it, but maybe it should have got into that article as well.
Okay, so we will make sure to send you the papers.
Thank you very much.
Thanks.
Okay, let's thank Professor John Miller again.
Thank you, Professor. We will leave the streaming open so you can watch the other lectures before, and I'll see you later. Thank you.